de tener la visita de Emmanuel Giroux. Entonces, Emmanuel Giroux es un geómetra que trabaja en geometría de contacto. Hizo la mayor parte de su carrera en Lyon. Fue invitado del Congreso Internacional en 2002 y ahora está trabajando en Montreal para un par de años. Y va a estar en México toda la semana. Para los interesados va a dar otra plática en Cuernavaca el jueves en la mañana. Y bueno, creo que ya nos va a hablar de The Geometry of Contact Elements.
Thank you, Pierre. Two things. First, I would like to apologize for speaking English, but I haven't spent enough time to Mexico to speak Spanish. So. And I also would like to thank very much Pepe Seade for inviting me to deliver this lecture. It's a great, great pleasure to be here, and I really thank him a lot. So, what I would like to do in this talk is essentially to explain how a very classical topic of mathematics, namely the study of the theory of plane curves, duality in plane curves, and the study of singularities of plane curves, has raised questions which are still open and are still studied by researchers today, and some of which have received recently solutions that involve quite sophisticated mathematics. So I don't want to go into this sophisticated mathematics, but I would like to explain the genesis of these theorems. So I'd like to discuss is duality in the theory of plane curves. I'm sure all of you have heard about duality, at least in the context of, let's say, vector spaces. But I would like to maybe to give a presentation of duality which is more concrete. And before that, since the main object I will consider in these talks are plane curve, I would like us to agree on what we mean by plane curve. So I will do that not with definitions and abstract things, but mainly with pictures. So, for example, here are three plane curves, which are, I'm sure you know. On the left, it's a parabola, then an ellipse, and then a hyperbola. So they are what we called conics, because you can obtain them as intersection of planes and a cone in the space. And what I just want to say about these curves is that they are smooth. I mean, you can draw them with a pen on a sheet of paper without stopping in a very fluent way. Of course, for the hyperbola, you need to draw two curves somehow, because you have two branches. Here are three other curves, and here you see appear some singularities of the curve. For example, if you draw the curve on the left, which is called a semi-cubic parabola, then you have to stop at some point with your pen and go back in the other direction. The curve in the middle is called a lemniscata, and it doesn't have any, so this sharp point you have on the left-hand curve is called a cusp. The lemniscata doesn't have any cusp, but you see that it has a self-intersection point. So if you draw it, you intersect the curve you already drew when you come back, okay? And finally, the curve on the right-hand side, which is called a swallowtail, because you can understand why, maybe. It has a self-intersection point and two cusps. So what is a way to represent curves in mathematics? A very, very general way of doing that is using parametrizations. For example, if you take this ellipse, you can define it as parametrized by the map which associate to any t, the point 2 cos t, 2 cosine t, and sine t. What does it mean to have a parametrized curve? It means that you consider the curve as consisting of points which move, well, let's say one point, which moves with time. And at each time, you have a point defined by two coordinates, which depends on t, x of t, and y of t. And of course, the same curve, you can present it. It admits several parameterization because just you can draw it slowly and then accelerate at some point, or just accelerate at other times and make a different, I mean, the movement is not the same. And just this difference in movement gives you different parameterizations. For example, for the cosine t, sine t, you can take these more algebraic formulas, 2 times 1 minus t2 over 1 plus t2, and then 2t over 1 plus t2. Well, another example for the lemniscata is given by parameterization. What is it, by the way? I forgot. Okay, I never use it, but okay, you can see it. And you can check that you get this, this shape of curve if you use this parameterization. Yes, okay. So, but what I mean is, so it's this parameterization business is a very general tool for describing a curve. Really, anything that moves in front, anything which is small enough to be identified with a point and which moves in front of your eyes, then it draws a parameterized curve with time on your retina. But what I want to explain now is that nature offers curves which are not parameterized curves, which are obtained differently. And here is an example which will be important for us. This is what is called an envelope. So let me explain this picture. So maybe it's a picture that you have already seen, at least this curve, this shape of curve. You can see it sometimes if you have a cup of tea, which is which is, let's say, suitably lightened. And let's try to explain. Suppose you have, here is a cup of tea. So this is the boundary of your cup. And the light comes from your left. And it goes down slightly. It's not, the rays are not completely horizontal, so it just doesn't meet this side of the cup, but it meets the other side. Right? Do you understand the picture? And there it's reflected. And because of the form of because you have a circle, which is the edge of the cup, the angle of reflection of this ray depends on the point where you touch the cup. And so the reflected rays have a direction which is, if you touch it at some point, cosine theta, sine theta, the reflected rays are by minus 2 cosine theta and 2 sine theta, and minus 2 sine theta. So what you see from this, these formulas just follows from the reflection laws, and at the beginning you had parallel rays coming, but after reflection they are no longer parallel, right? And so the light somehow concentrates along some curve, which is the curve you see, which is called a nephroid. And because you have the T, which make a kind of screen, you see this curve on the surface of. Is that clear? So that's and there are many In physics, you meet a lot of situations where you have curve presented in this way. Okay, so now okay. Now, what I want to discuss again is duality. So we'll forget about plane curve for a while and just explain duality in a very concrete setting. So it's a kind of game. Duality is a game which associates to any picture in a plane another picture in another plane. And the rule of the game is the following. If you take a line in the left-hand plane, which has coordinates x and y, and you take the line which is defined by the equation y equals ax minus b, then to this line, you just associate the point AB in the right-hand plane. Is that clear, the rule of the game? So let's do that and see a couple of examples. So here you take two lines on the left-hand side. The lines minus 2x plus 1 and the line defined by y equals 2x minus 3. So the corresponding points are minus 2, minus 1, and 2, 3. All right? And now, okay, you say, I have 2 points on the right-hand plane, so I have a line join them. And the equation of this line is b equals a plus 1. So now I can kind of iterate my game. So I have a line on the right-hand plane, so I can consider it as a point in the dual of this plane. So, and the point corresponding to this equation b equals a plus 1 should be 1 minus 1. And there what you observe is that this point with coordinate 1 minus 1 is indeed the intersection point of the two lines you add in the xy plane. So what does it mean? It means somehow that the dual plane of the right-hand plane is the initial plane, the left-hand plane. Right? Do you understand? So let's go on and see how it works. So here I take 6 lines, I think. 4? Just 4? Okay. 4 equations. I was lazy? I have 6 lines in the picture, okay. So you have the equations and then the corresponding point. And okay, that's just one example, but I can draw more. Here you have 8, I guess. And what you see is that, okay, I forgot to say something. Of course, you know that not all lines in the plane have an equation of the form y equals ax minus b. If you take this equation, then you will never have the vertical lines parallel to the y-axis. But what you see on this picture is that when you take lines whose slope increases to plus infinity, so they become more and more vertical, or it can also decrease to minus infinity, the points, the corresponding point, escape to infinity. So that exactly shows you that the vertical lines on the left-hand plane will correspond to some points at infinity on the right-hand plane. And you have to add this point at infinity on the right-hand plane. Otherwise, you only have part of the picture, right? If you want to have a complete picture, then you have to add points at infinity on the right-hand plane. And again, what you see is that all the lines in the left-hand plane on this picture intersect at a point. And what happens on the right-hand plane is that all corresponding points are lined up. And they are lined up on the line which corresponds to the intersection point on the left-hand plane. Okay, so as a kind of consequence, direct consequence of this observation, you have a reciprocity properties of this duality, which mean that here, for example, there is a triangle on the left-hand plane. So it has vertices, it has edges, and you have and you withdraw the dual triangle on the right-hand plane. And so the vertices of the right-hand plane correspond to the edges of the left-hand triangle, and the edges of the right-hand triangle correspond to the vertices of the left-hand triangle. So you have this reciprocity. Okay. So a few more remarks about what I was explaining about point at infinity. So you see, if you take parallel lines on the left-hand plane, so to have parallel lines just means that they have the same slope. So the corresponding point have a fixed coefficient A. And so they are lined up on a vertical line, right? So now consider the vertical lines in the left-hand plane. They are parallel. And so they correspond to points at infinity on the right-hand plane, as we explained before. And these points should be considered to be lined up because they correspond to a family of parallel lines. So you see that at infinity of the right-hand plane, what you have is something which is a line. And one more remark about these points at infinity. So for example, if you take parallel lines in the right-hand plane, now they have a common slope because they are parallel lines. And this slope is a point x, correspond to a value x in the left-hand plane. So these parallel lines in the right-hand plane define the vertical line in the left-hand plane, which is a point at infinity in the right-hand plane. And so you see that parallel lines, that just shows you that parallel lines actually intersect at the point at infinity. Well, and you can develop all these considerations, and what you get in fine is the definitions of the projective plane. So if you have heard about that, you can think of how it can be kind of constructed from this perspective. Okay, but now I want to sophisticate a little bit our games because lines and points is okay, but a bit boring. So here is a game now. We take a curve in the plane. So here is I take the parabola, y equals x squared. And it is a smooth curve, so at each point I have a tangent line. So, and here are a few of these tangents to the parabola. But I have a one parameter. I mean, for each point along the curve, and assume the curve is parameterized by, say, by time. For each time, I have a tangent. And so in the dual plane, I will get a point. So I can construct what is called the dual point, the dual curve. I have a curve in the plane. I look at its tangents, and I build a curve in the dual plane. And here is what I get with a parabola. I get a parabola, but the equation is slightly different. It's just b equals a squared over 2, over 4, sorry. So that's a bit disappointing because you start with a parabola and you end with a parabola. Okay, it's not quite the same, but not very different. So let's try with something else, just to be sure we're not doing too boring things. So here, take an ellipse. Ah, sorry. Sorry. Okay. Here's an ellipse, sorry. here's an ellipse with a few tangents, right? And so here you see something interesting, because on an ellipse, you have two vertical tangents. So what does it mean for the dual curve? It will have 2 points at infinity. Now, can you guess what's the dual curve? For students, my questions are only for students. Okay? What? Yes. So here it is. Okay? You see that exactly these two vertical lines correspond to the points at infinity of the hyperbola. Okay. Let's try to see mathematically how to define the dual curve. So you start with a curve which is parameterized by a map gamma from R to R2, which takes t and maps t to x of t and y of t. So you want to see how the tangent at a given point x of t and y of t is defined. So the tangent, okay. The equation of the tangent, so the claim is that the tangent at any point x of t, y of t is a set of point t such that the vector joining gamma of t to p, is vector p minus gamma of t, is collinear to gamma prime of t, or gamma dot t, right? And so you write the determinant of the two vectors. You say that it should vanish. And you get the formulas for the, you see that the tangent is actually defined by an equation y equal ax minus b, where a is just y dot over x dot, and b is x y dot minus y x dot over x dot. So you get a parametrization for the dual curve. Okay. Let's see a couple of other examples. Am I too fast, or is that okay so far? If you have questions, just don't hesitate asking. That's the point. We're coming to that. So first of all, what do you mean by singularities? So here is a curve. You know it, right? So it's just the graph of the function x squared, x cubed. You don't see? So it is a smooth curve. But do you see the tangent also, or just the curve? Okay. Okay. But it has something special. Well, if you look at tangents, what does happen? You see, the tangents rotate this way, and then here it stops, and it rotates in this direction, right? So what will happen for the dual curve? You see, exactly we had what you explained before. The movement of the tangent is given by something that goes just smoothly, and at some point it stops, and it goes back in the other direction. So what will you have in the dual curve? Okay. That's what you have. So, and kind of course, conversely, if you start with this curve, the dual curve will be the previous curve. So if you have a cusp and the curve, you will have an inflection point in the dual curve. So inflection point, what is by the way, what is the definition of an inflection point? It's a point where the curve somehow goes across the tangent line. Here is another example. So what you take is just the curve, which is a graph of this function 2x squared minus x4. And Is there anything special on this curve? This curve has what's called a bitangent, which means you have a tangent which touches at 2 points. And so what will it mean? What will it imply for the dual curve? And also you see that you have 2 inflection points on this curve, right? So what will be the dual curve? Yes, because you have this bitangent. So bitangent means you have a tangent in the initial curve, which I think you can see, or maybe here, which touches in 2 points. So this bitangent will give a point corresponding to intersecting things. Okay? Well, other questions about all these curves and dual curves? I think we will go to something different, precisely so. Right, so I just want to make a few remarks. If you take that's the thing about cusp and inflections, right? This slide, is that? Ah, ok. C'est la suélotée. Okay. So, the observation I want to make is that if you take a random curve in the plane, it has no cusps. Why is that? Because a cusp is a point where the 2 derivatives vanishes, right? And so that means that to have a cusp, you need to have a point where the x dot and y dot vanish. And these are 2 conditions for 1 parameter. So kind of, for a random curve, this will never happen. You can always slightly perturb the curve, change the functions x of t and y of t, so that they don't vanish at the same time. And the result of that is a random curve doesn't have any cusp point. What about inflection points? That's very different. Because if you have an inflection point, what does it mean? It means that, again, I said the definition is that the curve goes across its tangent. And somehow this means that the curvature of the curve vanishes at some point, which mathematically means that the 2 vectors gamma prime and gamma dot and gamma dot dot are collinear. So the determinant of these 2 vectors vanishes and the sign changes. And so you see the vanishing of these determinants, this is one equation. So you cannot avoid them in general. And if you have a curve which has an inflection point, and you perturb slightly the curve, you will still have inflection point. Because if you have a quantity that vanishes with a sign change, if you take functions which are very close in the C2 sense, means that not just the function is close, but the derivative and the second derivative are also close, then you will still have this change of sign. And so there is something weird here, because cusp for a curve correspond to inflection points for the dual curve. And so, since a curve doesn't have a curve in general, that means that the dual curve will not have inflection points in general. While since the curve, you cannot avoid inflection points, then the dual curve should have curves. And maybe here I should explain also one thing, which is the curves we have used are defined, were mostly defined as parametrized curves. And what does it mean? It means that the dual curve, so you take a parametrized curve and you look at the tangent at any point x of t, y of t. So you describe the family of tangents as parametrized by t. But the dual curve somehow, so you define a family of lines depending on t, and you obtain the dual curve as an envelope of this family of curves. So you see, what I mean is that plane curves are usually defined as parametrized curves, but dual curves somehow are not defined as parametrized curves. They are defined as envelopes, which is a very different way of describing a curve. Is that okay? So now, I would like to give one more example, which will be important for us later. Do you have it? Yes. So, it's a very simple thing. What we do here is we take a line in the plane, or again, we should rather think as a line is a projective plane, but for those who don't know what it is, in case, just think a line in the plane. And we will, so this is D, and we'll take a curve which kind of is a small deform, because when you take a line, the dual curve of a line is just one point, as we saw. No, so you just perturb a little bit this line. And I claim that what you get, provided the point at infinity in this curve is not an inflection point, you get the curve which is drawn in the picture. Why that? And let's say, yes?
Maybe this corresponds to an inflection.
Let me try to explain first. You will ask your question again in 2 minutes, okay? So, what do I want to say? Yes, so just one observation about this curve, what I want to explain with this picture, let's make a claim. And what I want to explain with this picture, if I take a deformation of a line in the plane, I get a curve that has at least 3 inflection points. Why that? So I pretend that it's a proof on the picture, but I have the curve which is here, like this C. Okay, so here you see the tangent of C at infinity is horizontal, right? So it's parallel to the line D, and that means that these two, the curve C actually intersects D at infinity, right? But now, the claim is that if I assume that this point at infinity is not an inflection point, or maybe first an observation, take 2 lines in the plane which intersect at some point. At infinity, so okay, you have the horizontal axis, and you take any other line, okay, with a small slope. They intersect at a point, so they don't intersect at infinity, right? And in the plane, what you see is that this line, which is slightly slanted, is on one side of the horizontal axis at near minus infinity, and on the other side at plus infinity, right? So the same observation applies here to explain why this C is on different side of its tangent at infinity, because the infinity is not an inflection point. So since it is not an inflection point, that means it doesn't intersect, it doesn't cross its tangent line at infinity, and because of that, it is on different sides. If I look in the plane, it is on different sides of its tangent at infinity. Is it clear? Pierre, what's your question? Okay, so good. And as no, okay, we can, but did you understand my explanation about the picture? Then I will explain. He is right. I mean, we can make this picture in very different ways. So, for example, I can make a deformation in which will not intersect D at infinity, right? Somehow it's more generic, it's even simpler, right? So, how will it look in that case? The tangent at infinity for the curve C will not be parallel, right? So it will be a line, but with some slope, okay? But again, because the curve, if I assume that the curve doesn't have an inflection point at infinity, then it will be on one side of its tangent here, and on the other side of its tangent on at the other end, right? So it will be, let's say, under, so it will have some minimum with respect to the curve, and then an inflection, a maximum, and then, so it will have again 3 inflection points. Do you agree, Pierre? No. If you don't agree, I don't go on. I stop here. So, no, well, the point is, so okay, just an observation. I assume that I take a line, okay? And I take let's say it's a horizontal axis. And I take a curve which is close to this line, okay? So it has, and it is tangent to this line at infinity, plus or minus. So, but assume it is above the line on both sides, right? Then you can just make a kind of Gaussian curve with a bump and then, right? But then, and here you only see 2 inflection points, right? But the point is that because it is above the line at infinity, it means that in the projective plane, it intersects the tangent at infinity. So there is a 3rd inflection point. And if you don't do this, if you assume that on one side it's above and the other side it's below, then you will have to have a minimum. So you will have a first inflection point between minus infinity and the minimum. Then you will have to go up to cross the line. You have a between the minimum and the maximum, you will have another inflection point. And then between the maximum and plus infinity, you have a 3rd inflection point. Do you get it? Or? So that's interesting, just to consider this picture from different points of view. Okay, so now I want to come to contact geometry somehow. And the idea is, in this context, is that we would like to have a space where we can see both a curve and the dual curve on the same picture somehow. So how to do that? We do that in this way, that we consider in the product of R2 with itself, we consider so you will have now 4 coordinates, x, y, a, b, and you just write the condition that the point x, y belongs to the line y equals ax minus b. Or conversely, by the way, it's the same as saying that the point AB belongs to the line b equals ax minus y. So you get this incidence manifold. So you have one condition in a fourth-dimensional space, so it's a three-dimensional space. And that's what is called the manifold of contact elements. But you have two projections to the plane R2. And moreover, you can identify this manifold just with R3, just because actually the coordinate B can be determined by these three others. So you see that it's somehow this V is the graph of a map defined on R3, maps x, y, A to x, y, A and B, which is AX minus Y. Okay, so you can really identify this space with R3. Now, what can we do with our curves? The claim is that if you take a curve in the plane, and then curve C in the plane, there is a unique curve C tilde in V, which has the property that it projects to the curve C in R2, and it projects in the R2 is coordinate XY, the XY plane, and it projects to the dual curve in the AB plane. And how is it defined? Just what you take as coordinate AB are the coordinates of the tangent line to the curve. Okay? So again, the manifold of contact elements, at each point, you consider all lines over each point xy. You take all lines containing this point. But here, you specify the curve, the line, which is the tangent line to the point, to the curve C at this point. Is that okay? So in this way, you define the lift of your curve. And the question now is, what are the geometric properties of this? Is that any curve in this manifold V, or does it have some specific properties? And yes. Yes, it will be algebraic. Yes. Yes, yes. So, what are the properties of this curve? Here, the main point is that, okay, so you have constructed, I explained how this C tilde is defined, just taking the tangent over any point xy, which is in the curve. I take the tangent to the curve at that point. Now, the claim is that among all lines passing through a given point xy, so you have the curve. You take a point on the curve, and what I claim is that among all lines through this point, the tangent is characterized by its slope, right? And the slope is just y dot over x dot. So you see, this line that this curve C tilde I have constructed has a property that inside, now you look at the curve C tilde in V. So at each point, this C tilde in V has a tangent line. And the claim is that this tangent line satisfies that, so you are at the point x of t, y of t, a of t, b of t, right? And that the tangent vector is defined by x dot of t, y dot of t, a dot of t, b dot of t. And it's not any vector. It has the properties that y dot of t is equal to a of t times x dot of t. And what I claim is that this condition actually means that this line, the tangent line to C tilde, lies in a very specific plane. defined by this condition that dy is equals to a dx. At any point x, y, a, b, you consider in the tangent space of V, this thing that is denoted by xi, x, y, a, which is a set of vectors, let's say delta x, delta y, delta a, such that delta y is just a times delta x. And the claim is that it's one equation is three-dimensional space, tangent space, so it's a plane. And the curve C tilde has to be tangent to this plane. Now here is the definition that this plane, at each point of V, you have a plane, and this plane distribution is called the contact structure. And the curve, now any curve which is tangent to this distribution, which is the case of C tilde, is called the Legendrian curve. Okay, that's very abstract thing, so let's look at how it looks. Okay, so this is the picture of the contact structure in R3. So let's look at it closely. So you see the coordinates, right? So if I remember correctly what Patrick told me, but the a-axis is coming slightly to the right, no? And the x-axis is, well, is there a yeah, x is pointing to us, a is directed to the right, right? And y is vertical. So you see, I will try to explain physically how it looks. So you have the, well, let me try to be consistent with x is going to you, a is there, and y is there, right? So now you take the origin here. You are at the origin. The origin is dy equal a dx, but a is 0. So this is an horizontal plane. And all along the x-axis here, this will be horizontal because a is 0. And actually, this plane field is invariant under vertical translation. So you just need to define it near the horizontal plane. So here it's horizontal, and then it does that when you go along the a-axis, it rotates, and it tends to infinity, at infinity. And the opposite here. Do you understand the picture now? So just a bit of so you see it's a quite twisted plane field, plane distribution. So, for example, you have a plane field, what's called a plane field, which at each point you have a plane in the tangent space. Natural, what you can expect from such a thing is maybe I can find, you know, when you have, I'm sure you at least for those who have classes by Anna about differential equation, you know that if at each point you take a vector, then you have, this defines a differential equation, and then you get integral curves when you have a vector field. So a natural question is, now here I have a plane field. Do I have integral surfaces? Meaning surfaces, pieces of surfaces, that are tangent to this plane at each of their points. You understand the question? So, and the proposition is that you cannot find any such piece of surface because the plane field is much too twisted. And let's try to explain that. If you have a surface which is tangent to this plane field at any of these points, because you see, the plane field, let me remind, it's horizontal along the x-axis, and when you go to infinity, it tends to the vertical, but it's never vertical. Since it's never vertical, if it is a tangent space to some surface, by the implicit function theorem, this surface is defined as a graph, at least locally, it's given by y is a function of x and a. Right? So the tangent space, the tangent plane to this surface, is defined by dy equals partial differential of f with respect to x times dx plus partial differential with respect to a times dA. But now you want this plane, to agree with the plane defined by dy equals a dx. Okay? And so this means that you can identify the two equations. So that means that you will have the differential with respect to f, differential of f with respect to x should be equal to a, and the differential of f with respect to a should be 0. But now, I'm sure you have been taught that when you take a smooth function, and actually you can argue that this function should be smooth, then when you take the mixed second derivatives, they should be equal. But here, in one case, if you derive first with respect to x and then with respect to a, you will find 1. And if you differentiate in the other order, you will get 0. So you get a contradiction. Right? So there can be no such surface. Okay? So now, okay, I should finish soon. So I just want to explain one result, which is very recent, and which answers a conjecture of Arnold, that Arnold made, I think, in the 90s at some point. So let's come back to this deformation of line I explained before. So if you have a line in the plane, you know that the dual curve is a point. And when you take a small deformation of this line, you know that it has at least 3 inflection points, which means, by what we explained before, that the dual curve should have at least 3 cusps. Okay? So, and the question now, okay, that's for a small deformation. But Arnold said, okay, now what I will do the following. Instead of just taking this small deformation and taking this lift is a Legendrian curve. Now, this curve, I will allow me to deform it as much as I want. Make any deformation of this Legendrian curve, provided it remains a Legendrian curve at any time. Is it true that I still have at least 3 cusps, or can I cancel some cusps so as to have just 1 or something like that? And his conjecture was that it's impossible. So while it's a deformation, it will always have at least 3 cusps. And this was proved very recently by Stéphane Giroux using quite sophisticated tools which are called the micro-local theory of sheaves. So that was just to explain that very simple question can lead to very complicated mathematics, and I think I will stop on this very positive way of thinking. Thank you.
¿Hay preguntas?
This duality can be generalized to Riemann surfaces?
This duality is really duality for projective spaces. So it's, but what you can do, what is true is that for any manifold, you can consider there is an associated manifold of contact elements. We just suppose you have a manifold, n-dimensional manifold, and you just take at each point, you consider in the tangent space all hyperplanes in this tangent space. And these form a bundle over your original manifold, which is called the tangent bundle, the contact element bundle of the manifold. What is specific to the projective case is that this manifold of contact elements embeds into the product of the projective space with its dual. And there is no such structure in general. Right? Do you understand? Yes. Yes. We don't have any such classification of Legendrian knots or things. What's interesting, maybe I should explain here, because I said that when you have a plane curve, let's say with a cusp somewhere, you can approximate it by something with no cusp point, right? But the point is that when you do this approximation, you may think, what's going on there? Because the Legendrian approximation, that means that I will approximate, now I take the lift of this curve. I get two Legendrian curves, and one projects to something with a cusp, and a very close thing will, well, and you take, let's say, you approximate. So you get two Legendrian curves, and now you can project and you take the dual curves. One will have an inflection point, and the other will not, because there is no cusp. So how could this inflection disappear? You explained that it could not disappear. Okay? But the point is that when you do this approximation, actually the Legendrian curve is very far from it's not, the approximation is not an approximation on the level of Legendrian curves. Okay. Thank you very much for your attention.